Hello, everyone. I am Ankit Agrawal. I work as a system software engineer at NVIDIA, and I'm part of the vGPU team, NVIDIA. So I'll talk about the vGPU architecture on the Grace Blackwell systems. Um, uh, Talk about features like EGM, how do we extend that feature to virtualization, and the upstreaming status for those. So going to the agenda, we'll start with the Grace Blackwell Superchip architecture, the salient feature of the system. Then we'll move on to the how we support SRIO vGPU on this architecture on Grace Blackwell. Then we'll go a little bit ahead on and discuss on extended GPU memory feature, which is the Grace Blackwell supports this. Go into the details of that, what that is, and what's the features on that. Then we will move on to the design on for virtualization as to how we extend this feature to the virtualization realm. And lastly, we'll discuss the current path status on the various things that are here. So, so first I'll start with the architecture for Grace Blackwell, right? So, so this is what you see on the left is like a typical Grace Blackwell node, right? It's a dual socket 4 GPU system. The CPUs are ARM based, and each socket has 2 GPUs, right? So the total it's 4 GPU system. So the primary feature of this architecture is that the CPU and GPU can coherently access each other. So what that means is that the GPU memory can actually be added to the kernel, and the kernel becomes the manages all the GPU memory, and any let's say allocations on the GPU are actually handled by the Linux MM, and this is assisted by the ATS and by the support of the ATS and PASID, right? So the CPU memory is accessible from the GPU. There could be two parts to that, right? The first one is, let's say, if you're using a CUDA APIs, so they would, if that is executed, that would result in the GPU mappings to the CPU allocations. So if any access happens, it would go through the GPU MMU and then on to the SMMU. However, if it's the allocation is just malloc based, right, a map based, and the GPU does not have any mapping, it would still go use the PASID ATS path to access it. Right? So essentially, that way, any allocation on the CPU are accessible to GPU. One thing is that the GPU memory is not in the EFI memory map, and hence, when the system boots up, the memory is not visible at boot up, right? And the information about this GPU memory properties are present in the ACPI tables and can be fetched by various modules. And this, like I said, this is like the basic unit. Now, several of these units could be stacked up and to construct a large system. For example, there is GB200 NVL72, where you can stack up 18 of this, where each of the GPUs are connected over the fabric. So going ahead to like the architecture for that for a vGPU, right? So we have kept the architecture almost similar to what we do for x86 systems. There are some subtle changes that I'll explain, but overall the architecture is very much similar. So for example, the NVIDIA.ko on the host, right? It's the primary driver that manages the GPU workloads. It also communicates with the GPU to offload the work, right? The thing that are done different, I've put it in italics, well, very neatly. So, so what it does is fetches the GPU memory information from the ACPI, right? That way it knows the SPA, base SPA, and the size of the GPU memory. Then the NVIDIA vGPU VFIO, it is an out-of-tree open source module, right? It is an equivalent to a VFI PCI variant module in terms of functionality. It communicates with QEMU to expose the GPU VF's PCI resources, right? then it exposes the GPU memory as the VF par2, right? So this is essentially region 4 and 5 on the PCI. Then Chemo just emulate the VM's vGPU device as usual, as in on x86, similar to that. It fetches the VF resources and does the mapping. And lastly, it prepares the VM's ACPI tables, right? It makes certain changes to it. I'll explain later, but essentially that is the part that is different. Within the VM, the primary driver, again, there is NVIDIA.ko, which is the driver that manages the SRIB vGPU within the VM. It communicates and sends workloads to the GPU. The thing is that it hot plugs this GPU memory within the VM to the VM kernel, right? So the behavior of the VM is kept almost identical to, let's say, a bare metal system on the Grace Blackwell. So the GPU memory would be added within the VM to the VM kernel. When I say add, it means hot plug essentially. Going through the vGPU flow, right? So what happens is that just NVIDIA services starts, right? And during that time, the NVIDIA.ko loads. The thing that is special, that is done specially for the Grace Blackwell, is it put in blue, right? So when the NVIDIA.ko loads, the GPU memory size and SP are fetched from the ACPI tables, right? And it saves it. Then the next thing you do is you enable the VFs, right? Then you check for the vGPU profile availability. So essentially, it checks whether there are enough resources on the GPU to be able to create a vGPU, right? And if there's a go ahead there, then the CPU, the vGPU instance is created by and associated essentially to a VF. Then you go ahead and launch the VM, right? Then after launching the VM boots up, and within the VM the NVIDIA services starts, and again the same thing happens in the sense that NVIDIA.ko loads, and this time it adds the GPU memory within the VM to the kernel, right? And once that is done, the setup is all done, and then you can start the apps. So quickly going through the vGPU architecture, right? Step by step sequence, what happens, right? So first of the thing is you try to create a vGPU, right? That request comes to NVIDIA vGPU VFIO. It checks whether it's okay to create the vGPU device with NVIDIA.ko, right? If it is good, then you can start boot up the VM. That would result in an open call to the NVIDIA vGPU VFIO, right? And which would send a start the vGPU request to the NVIDIA.ko module. When that happens, the GPU memory is allocated by the NVIDIA.ko. That would be for the virtual GPU, right? And then NVIDIA.ko informs the base SPA and the size of the allocation that it did. Then it goes and save the GPU memory info. And interestingly, it exposed the GPU memory that is associated to the vGPU as device bar, right? So Chemo goes through the normal process and essentially tries to fetch it to fetch all the regions that are there, and at that point it would discover this bar2 region, right, which is essentially mapped to the GPU memory. So when it tries to request like what is the region information, so the vGPU memory size is returned to it, right? And then it would try to do the mapping to the bar2 within the in the bar2, right? And that request would comes into the NVIDIA vGPU VFIO, which would essentially map that to the SPA of the GPU memory. So within the VM, it would be visible as bar2, but actually on the host, it would be mapped to the GPU SPA. Another thing it does is it adds the PXM nodes to the SRAT table. So what this helps is it essentially makes the VM create separate nodes for the GPU, so when the VM kernel sees different proximity domain nodes, it would allocate resources or essentially creates node within the VM. Those would be initially memoryless NUMA nodes. So the VM boots up and it would see there would be load module request, and then first thing it would do is fetch for the proximity domain, fetch proximity domain indexes. Then it would ask the kernel to convert that into the NUMA node ID, and it would then fetch the bar2 information. Remember that this is mapped to the GPU memory, right? And then it would hot plug that as a separate NUMA node. So within the VM, after all of this happens, the GPU memory is essentially added within the VM, and the Linux MM can within the VM, the Linux MM can can allocate on it. So going through the extended GPU memory feature. So in this feature, essentially, this is a mechanism by which you can do allocations on the CPU memory, right? And then that allocation can actually be accessed across the from the GPUs across sockets or even across different nodes, right? So like I mentioned earlier, right? Various Grace Blackwell units are stacked with each other, but the GPUs are connected over the NV switch fabric. So even if it's a remote system, the GPUs are actually connected. So that path is made use of in for this feature, right? So like I said, right, so the GPU, the allocation could be accessed from across the socket or even across a different system, entirely different system that is part of this large set of systems. And obviously, it can also access the local memory. So essentially, allocation of the CPU can also be accessed from the local GPU. On the right, you can see the picture of various connections, data paths that are there. I've kept the CPU to CPU connections as dotted because the CPU may be on the same system or on a different system where they're not directly connected. But GPUs would always be connected, right? And then it would follow the path that is mentioned in the red, right? So it would go from one GPU to the other GPU, irrespective whether the GPU is on the same system on a different socket or a completely different system. And another thing is that the single allocation actually is limited. The single EGM allocation on the CPU is limited to the size of the memory on a single CPU NUMA node. Then this remote CPU memory is exposed via EGM. It can be accessed, like I said, like it would be accessed via NVLink NV switch fabric, and it would follow the standard GPU model. But this is like an added feature. The original capabilities are still retained. So all the native GPU operation will work as usual. All CPU accesses will work as usual, right? So this kind of adds to the functionality. To enable this mode, essentially, you have to you are given a flag in SBIOS that you can flip to enable this mode, right? And the base and size of this EGM region would be exposed through the ACPI properties, right? And the presence of these properties serves as a cue for the software to know that the EGM is enabled or not. In other words, if you do not enable in SBIOS, there won't be any EGM properties in the ACPI table. So on the left side, if you can see that there's a bare metal memory map, right? So the CPU memory and GPU memory, right? And the entire system memory is accessible to the GPU as EGM. So what that means is that you can do any allocation anywhere on the CPU memory. Obviously, kernel would do it, but allocation can be made anywhere, and the GPU would be able to access it. Virtualization is much more interesting. Here you are provided because the host memory is shared between the hypervisor and the VM, right? So you are given a flag in the SBIOS where you can set how much hypervisor memory do you want, right? And for example, if you set 32 gig, that size of memory would be visible to the hypervisor when it boots up. Yeah, and the rest of the region that is there would be invisible to the hypervisor. I mean, it is accessible, but it won't. The hypervisor won't be directly available. It won't be directly visible to the hypervisor because it's not added or it's not aware of it because it's not part of the EFI memory map. Yeah, so I've interchangeably used this hypervisor invisible region as EGM in the patches as well, and I'll talk similarly here. But when I say EGM region, I would be actually be referring to this hypervisor invisible region. Um, yeah, and essentially this hypervisor invisible region that becomes the system memory for the VM. So when the VM boots up, again it would see the CPU memory and the GPU memory, right? And but the behavior would be very similar to on bare metal. So what that means is that you can do allocation on the CPU memory within the VM, right? And subject to obviously VM kernel's ability to do the allocation, and then the GPU could uh, access that CPU memory. So going through the design, so I've grayed out the part that is actually we already discussed, right? So it is relevant to EGM as well, but since we already discussed, it won't be part of this discussion, this particular discussion. Um, so on the host, for example, if you see NVIDIA vGPU VFIO, it would do, okay, so first of all, this is essentially the architecture to extend this EGM feature to virtualization, right? And this design is actually similar whether you are using vGPU or even device assign the GPU to the VM. I have kept it for vGPU, but the design is identical for device assignment. The counterpart for this NVIDIA vGPU VFIO for device assignment is the NV Grace GPU module, which is already upstreamed. All right, so the NVIDIA vGPU VFIO module, it has a responsibility to read the EGM properties from the ACPI tables. Again, the size and the base SPA, right? Then it would build the data structure and save the EGM information, whatever it gathered. So remember that there is one EGM region for every socket, right? So if it's a 2-socket system that I just described, there would be 2 unique EGM regions. Right? And yeah, so then the NVIDIA vGPU VFIO would create an auxiliary EGM device, right? And that device would be per unique EGM region. Yeah, so then the NV Grace EGM, we also added this module. The patch series I posted a few hours back. Essentially, this is an auxiliary driver that acts or binds on the binds to the EGM device. What it does then is it creates a dev EGMX care device driver and expose the file ops for user space, user mode applications such as schema to use and map to the EGM and essentially manage the EGM memory. Then QEMU, right? So the QEMU would open. So this device that I just mentioned, right? That would be passed to EGM passed to QEMU as an argument, as a memory backend file argument, right? So when the QEMU is started, it would try to do an mmap, and it becomes a system memory. So so it would try to do mmap, which would be handled by the NV Grace EGM module. And then lastly, it is responsible to populate the EGM properties. Like in this case, it would be IPA, right? And size for the VM ACPI. So we have tried to keep keep the behavior similar to a bare metal system. So the EGM properties would be exposed through the VM ACPI. And within the VM, again, the NVIDIA.ko would read the EGM properties as usual from the ACPI table, as it does on bare metal, and it would enable the EGM stack. And after that, any EGM application that you run would be able to do the allocation. Going to the design, so if you can see there, I've mentioned NV Grace vGPU VFIO and NV Grace GPU. Not to confuse that. I mean, it is just that the design is identical, but NVIDIA vGPU VFIO is handling for the vGPU case, whilst NV Grace GPU is for the device assignment. But the design is identical. So So the the NVIDIA vGPU VFIO module would first fetch the EGM, SP, and size from the host ACPI tables, right? Then it would create an auxiliary device as soon as it notices a new region, and it saves the EGM info in a shared structure. The structure would be shared with the auxiliary device, right? So it puts that information in the auxiliary in the shared structure. Then NVGrace EGM would bind to this EGM device, auxiliary device. Um, then next step it would do is, will again, like I mentioned, it would create the dev EGMX schedule for EGM region and expose some file ops to manage this EGM memory. Then key move process would be started, and this dev EGMX would be provided as an argument. So it would try to do an open, and that would result in uh, the request landing in the NVGrace EGM, which would clear the host, which will clear the EGM region that is assigned to the VM, because because it is managing the GPU. So because it is managing the EGM region, so before giving it to the VM, it must clear it. So that is what it does. Then the request for mmap comes into dev EGMX, which result in again the handling by NVGrace EGM, which would map it to the host EGM region. And lastly, it populates the VM's EGM base IPA and size to the VM's ACPI tables. So the VM boots up, it would then just fetch the EGM IPA and size and enable the EGM stack. Say that again. No, it would be that it would be only the EGM. Oh yeah, the question is like, would there be any more other memory other than EGM? So essentially, the entire CPU memory, right, that is passed to it, it would be passed to the EGM region, and or any allocation and on part of any of the CPU memory, EGM allocations can be done. Right. So as I mentioned, right, this EGM region is hidden from the from the host, right? So who manages if there are who manages that when there are retired pages on the EGM region, right? So essentially we have handled this in a way that UFI would actually have the list of all the retired pages that it is aware of. What it does is it puts it puts the list of all the retired pages in a region and exposes the SPA of the region through the ACPI property. So NVGrace EGM, it would be aware of. So it would then fetch this information, the list of the pages, and save it in its in the NVGrace in itself, in its data. Yeah, and again, this in order to communicate the list to a user space, we have added a ioctl file ops ioctl that is associated with the dev EGMX. So the user space process could connect could send an ioctl and ask for the list of the retired pages, and then save it for further processing. Then within the QEMU, it makes a note of all these retired pages, and it uses the FDT to essentially create memory regions, and it skips all these retired pages so that it's not visible. So essentially the memory regions are created by skipping these retired pages. So when the VM boots up, the UFI discovers all these memory regions and skips the retired pages out of it. So the patch status, the first thing is that the KVM patch to map the GPU memory as cacheable, that is in. Earlier it used to be mapped as device. Now it can be mapped as cacheable because we need properties like unaligned accesses and prefetching and all the good stuff with the normal memory, and it is actually normal memory. So now it is being tagged with cacheable. The IOMMU FD support is also in now, which is also a dependency. Just the honorable mention that NV Grace module, GPU module, is already in tree. Whatever I discussed, there is a lot of similarity for device assignment, and that part is already inside the is in tree. In terms of the ongoing project, the EGM support, the RFC is posted, so folks can wanna take a look, they can. Then the next step is the ECC support for the non-struct pages, because these pages are, the mapping is actually remap PFN range, it's a PFN map pages. So we need ECC support for that. So that is also under the works. The next thing is the DMA buff exporter that we need. So essentially to export the GPU memory from export the GPU memory from the VFI PCI to the IOMMU FD. That is still in the works, and folks at NVIDIA are working on that. Then the counterpart would be the DMA buff importer in IOMMU FD. That would be next that those folks would pick up. And again, the huge PT support that was added earlier this year, we want to add support for that. So that is next. That is in the pipeline for the future. For QEMU, we have added the ACPI generic initiator object to add the proximity, to allow adding the proximity domains. So that is already in. Then the ACPI EGM memory object to populate the EGM properties through VACPI. That is also in the works still. So it's an ongoing part. Then the nested, it also has dependency on nested page tables. So that is also under the works right now. The folks at NVIDIA are working on that. And then lastly, the PASID capability needs to be exposed. So that is also under the works right now. Yeah, that's all. So so essentially, when would G's model will start using this? So it is in the works right now. So that is part of the plan. For now, we have done with the current architecture where we have to make use of the NVIDIA vGPU VFI, right? So we demonstrated this technology on that, but that would be part of our work to move it to the G's module. Yeah. Yeah, eventually we would want to, do that, yeah. Yes. So I'm not looking at that work. Actually, I'm not entirely sure. So the question is, what's the story on confidential computing with this, right? So I'm not sure right now at this point. All right, there are no more questions.